All right, so we are here to talk about logarithmic functions today. So we previously introduced the exponential functions, and we noted at that time that the exponential functions were one-to-one, meaning for every input there's a unique output. If you remember the graphs of the exponential functions, right, it either looked like something like this, right? If this is a to the x, for a being greater than 1, remember we pass through the y-axis right at 1, 0, 1 is the y-intercept. Or the graph looks like this, for a between 0 and 1. And in either case, if we draw any horizontal line, we will hit the graph only once. So if you remember, we talked about one-to-one functions means it passes the horizontal line test. And what that means is for every input, there's a unique output. Okay, so for every input, there's a unique output. And in that case, what's that mean? It means there is an inverse function, if you remember, when we were talking about inverse functions. And so what is the inverse function to the exponential function with base a? Remember, the value of a is greater than 0 and not equal to 1. Well, we call these functions the logarithmic functions with base a. So for every base a, for every real base a that's greater than 0 and not equal to 1, there is a unique logarithmic function, we say, which is its inverse with that same base. And this is the way we denote it. So first of all, the inverse function, remember, we use this little superscript -1 to indicate inverse functions. This is the way we abbreviate the logarithmic function with base a. That whole expression is condensed down to just log with a subscript a. So the subscript kind of makes sense, you know, because in the exponential functions we have a superscript and exponent. So kind of like to look at it as a subscript to undo that in a sense. Just notation, but log base a and then of x. Now typically if we're writing a function, this is the name of the function. This is the name of the function. This is like f or g or h, right? This is the name. This is not a quantity by itself. So when we put in parentheses x here, this is not multiplication. This says take x and plug it into this function. This is the name of the function. And we'll talk about how to find outputs for this function. But a lot of times these parentheses disappear and we just write it this way. Okay, so remember, this is log base a of x is what this means. This is not log a times x. So log base a is not a quantity that we can divide by, multiply by, etc. It is the name of the function. Okay, so now we can define this, these functions. If a is greater than 0, again, not equal to 1, we define the logarithmic function with base a this way. So how do we determine outputs? Log base a of x equals y if and only if a to the y equals x. Right? So take a look at this. What is y? Y is the logarithm, we say. The value of the logarithm when I plug in x is y. And so what is a logarithm? What is y in this problem? What is y? It is an exponent. Right? If you don't get anything, make sure you get this. A logarithm is an exponent. A logarithm is a power. That's what a logarithm is. It's the exponent on the base, right? Whatever your base is, base a, it's the exponent on a that we need in order to get the input, in order to get x. Okay, so that's what we're saying here. Log base a of x is the power to which a must be raised to in order to get x. All right, so log base a of x is a power or exponent. So when evaluating logarithms, it's much easier to think about its so-called exponential form, right? This is the logarithmic form. This is the exponential form. So you've got to be able to write in between these forms. It's very important. So you're going to practice that. That's part of the homework. For instance, log base 2 of 8 equals 3. Since what? The base is 2, right? Raised to what? The exponent is 3. That's the logarithm. Is equal to what? To 8. Okay. Let's just practice a few more here real quick. What if I had log base a of 5 equals negative 2. I'll just make something up here. What if we have log base a of 5 equals negative 2? That's my logarithm form. What would the corresponding exponential form be? Well, what's the base? The base is a. What's the logarithm? The output to the logarithm is negative 2, and the logarithm is what? What is a logarithm again? An exponent. What is a logarithm? It is an exponent. It's the exponent what? On the base. The base is a. Right? And that's going to equal your input in this case, right? So again, log base a of x equals y. What is y again? That is the exponent, a to the y equals x. You've got to be able to freely go between these two expressions. Okay, here's another one. What if I have 3 to the b power equals 100? That's the exponential form. Can you write that in logarithmic form? Well, log base what? What's the base? The base is 3. So log base 3 of what? Log base 3 of what? Well, what are we getting as an output here? We're getting 100, right? Getting 100 as our output, and so that's the input to the logarithm. Equals what? Remember, what is the logarithm? What is log base 3 of 100? It's the exponent on the base 3 needed to get 100. So it's b. Okay. So you've got to practice being able to write in between these two forms. And so if we're going to evaluate logarithms, then again, it's helpful to write in exponential form, right? So I say, what is log base 2 of 8? I don't know until I look at it from this perspective. Then I know, oh, 2 to what power equals 8? Answer 3. All right, let's look at some examples. And we should be doing this without the help of any calculator. Okay, so what is log base 3 of 9? Okay, let me call that x for right now. What is that? Well, if we go and write it in exponential form, what do we get? We get the base is 3, right? What is the exponent on the base? That's the logarithm. That's what x is, right? Equals what? The input to the logarithm, which is 9. So now in this form, I think you can answer the question. What's the value of x? 3 to what power equals 9? And I think you all say 2, right? 3 squared is 9. And that means log base 3 of 9 is 2. What's log base 5 of 1? Well, here the base is 5. What I'm looking for is the exponent. We'll call that x. And that's got to equal 1. So 5 to what power equals 1? The answer, 0. In fact, that's real important. Regardless of the bases, log base anything of 1 has to be 0, because any base, raised to the 0 power is 1. So it doesn't matter what the base is in this case. We always get that same output if you input 1 to any log function of any base. What's log base 10 of 1,000? The base is 10. Looking for the logarithm, the exponent, to give me what? 1,000. So what's the answer there? 10 to what power is 1,000? Well, 10 to the first is 10, 10 squared is 100, 10 cubed is 1,000. So the exponent on the base 10 needed to get 1,000 is 3. What's the exponent on the base 3 needed to get 1/27th? Well, 3 to the x equals 1/27th. That's a little strange. What in the world could that be? I know if I put it to the third power, 3 cubed is 27. So what am I going to get 1/27th? Well, remember, this is the same thing as 1 divided by what? 3 cubed is 27. But 1 divided by 3 cubed is 3 to what power? What do we do when we have a reciprocal here? Negative exponent, right? 3 to the negative 3 power is 1 divided by 3 cubed is 1/27th. So this tells me that the value of x is negative. So we can have negative exponents, remember? We can have negative exponents. So 3 to the negative 3 power is 1/27. So here's a real toughie. 12 is the base. 12 to what power is 12? It's log base 12 of 12. What's the power of 12 needed to get 12? Well, that's pretty obvious. X is 1, right? So log base 12 of 12 is 1. What's log of base 1/2 of 2? So 1/2 to some power is equal to 2. And what's that going to be? It's really 1/2 to 2 is the reciprocal. How do we get the reciprocal? -1. Good. So 1/2 to the -1 power is 2 over 1, if you want to write that way, to the first power, which is just 2. What about this one here? The base here is 16. What's the power of 16 needed to get 4? What power would that be? What power would that be? Well, 16 to 4 makes me think of what? Taking the square root. How do I take the square root? By letting x be 1/2, right? 16 to the 1/2 power is the square root of 16, which is indeed 4. So the power on the base is 1/2. Okay? And so that's how we can determine logarithms. Now, a problem will be is, what if I want to take log base 3 of 10? Then I've got 3 to the x equals 10. What's the power of 3 needed to get 10? Well, 10 is not a multiple of 3, and so that's going to be a little tricky, and that's where we're going to talk about using logarithmic functions later on to approximate those values. Okay. Right now, that's the way we find logarithms, the ones that we can find anyway. So let's look at the logarithmic functions themselves graphically. So recall that the graphs of the inverse functions, if you remember, we finished up that section talking about how the reflections of each other are about the line y equal x. Okay, and we're going to look at that in a minute. Further, recall that the domain of a function is the range of the inverse function, and the range of the function is the domain of the inverse function. So, when we look at the function f of x equals log base a of x, it has the following properties. The domain of our log functions is the same as the range of our exponential functions. Do you remember what the range of the exponential functions was? Everything greater than 0. So this is now the domain of our logarithmic functions. And this adds a little twist into the question about the domain of functions, and we'll look at this later as well. But whatever I plug into this function has to be greater than 0. Okay? Because why? Because if I take any base and raise it to any power, I'm going to get a positive result. Remember, our bases here are always positive. The base a, right? Remember, in the definition, the base a is positive, always. What's the range of our log functions? The same as the domain of our exponential functions, which was all real numbers. And notice I'm getting that. Look at the outputs I'm getting here. The outputs I'm getting are positive numbers, 0, negative numbers, right? I get any real number I can get as an output to the log functions. Now, here's what's interesting. Because the graphs of inverse functions are reflections about the line y equal x, right? The line y equal x is sort of a line of slope 1, sort of a 45-degree angle with the x-axis. And if I do a reflection about that, and I have the exponential functions, remember, had horizontal asymptotes. Say this green pen represents the x-axis. When I do a reflection in this this line here, what we end up with is a vertical line. So our horizontal asymptotes become vertical asymptotes. And so the horizontal asymptote of y equals 0 becomes a vertical asymptote of x equals 0. And then what happens when we reflect about the line y equal x, we just change the x and y coordinates. And so the point on the exponential functions, if you remember, was the y-intercept 0, 1. We'll change the order, you get 1, 0. That's the x-intercept. And we saw that up here, right, when we said log base 5 of 1 is 0. Well, log base anything, if I put any base down here of 1, I get 0, because any base to the 0 power is going to give me 1. So that's for all the logarithmic functions. When you plug in 1, the output is 0. Now, the graph of log base a of x is increasing when a is greater than 0, and it is decreasing when a is between 0 and 1. It's very similar to our exponential functions. Okay, so again, just like the exponential functions, you need to know these facts. These facts have to be known. All right, let's look at the graph of some logarithmic functions. We'll start with, we'll do this one, log base 2 of x. Okay, and I'm going to graph them on the same axis. So first of all, we did this one last time. This is the graph, well, this is a table of some of the values for the function f of x equals 2 to the x, if you remember. So let me plot those points. At -2, here's -2. This, be careful, this is 1, 2, so 1/4 is, here's a half, here's a fourth, and so -2, we're at 1/4. At -1, which is right here, be careful, -2, -1, we get a half. A half is right here, that's 1, so half is right there. At 0, we get 1. At 1, we get, here's 1, we get 2. At 2, we get 4. And at 3, right, 2 cubed is 8, so 3 we go all the way up here. So if I sketch that graph, there's our exponential function 2 to the x. Okay, rapidly grows up. Now, how do we get the graph for log base 2 of x? Well, remember, we said that they're inverses of each other, and that means they're reflections about the line y equal x. Let me just put the graph of y equal x on here for perspective. Do just a dashed line here. Okay, so y equals x, there's that line. Now, what does that mean if I do a reflection? It means the x-y pair, right, becomes what? We change the order. So now it becomes, instead of -2 comma 1/4, it becomes 1/4 comma what? -2. And this is the inverse relationship between these two functions. If I raise 2 to the -2 power, I get 1/4. Therefore, if I take the log base 2 of 1/4, I get -2. See how they cancel each other out? That is exactly the inverse relationship that we're talking about right here, right? So if I plug x, well, let's go over here. If I plug y into the exponential function, I get out x. If I plug x into the logarithmic function, I get back to y. Right? That's exactly the relationship here. So 2 to the -1 power is 1/2. Therefore, log base 2 of 1/2 is what? -1. 2 to the 0 power is 1. Therefore, log base 2 of 1 is 0. 2 to the first power is 2. Therefore, log base 2 of 2 is 1. And so on. So log base 2 of 4, the power of 4 needed to get 2 is 2. 2 squared is 4. The power of 2 needed to get 8 is 3. 2 cubed is 8. All right, so let's plot these points and let's see what this graph looks like. Do it in a different color. So notice the values of x we can have are only positive values, right? So at 1/4, x is 1/4, here's x equal 1, here's x equal 1/4. The output is -2, so we're down here. At a half, that's 1, so a half is going to be right here, we're at -1. At 1, there's 1, we're 0. At 2, we're 1. Here's 1. So at 2, we're 1. At 4, we're 2. And then 8, we're 3. Okay. And here's the logarithmic function. Now, do these two functions look like reflections about the y x to you? Rotate that around. Does that look like they're reflections? Yeah. All we've done is swap the x and y coordinates going from one graph to the other. That's what it means to be a reflection about the line y equal x. Also notice the factors that we talked about. The domain of the blue exponential functions all real numbers, right? I can plug any value of x in. And the range is what? Everything greater than 0. But for the logarithmic function, the opposite is true in a sense, right? The domain is everything greater than 0, which is the same as the range of our exponential function. But the range of the logarithmic function is all real numbers, right? Notice this keeps going up to infinity, and this down here is we're approaching a vertical asymptote of x equals 0. The y-axis is a vertical asymptote. This keeps getting more and more negative as x gets closer and closer to 0, and as opposed to the horizontal asymptote for our exponential function. Right? And then the y-intercept for the exponential function is 0, 1, and that's an x-intercept for the logarithmic function, 1, 0. So this is a general relationship. So here's some, in general, if b is greater than 0, and again I'll just, let me just highlight this real lightly. This is our line y equal x in both of these cases. All right. So here is the graph of b to the x if b is greater than 1, and this is the graph of log base b of x. So just like the one we just did where b was 2, right, we have the same situation. But if b is any positive number or any number greater than 1, then there's the graph of b to the x, here's the graph of log base b of x. Notice they're both increasing over their domains. But if b is between 0 and 1, remember this is b to the x, this solid line, and this is log base b of x. Notice it's decreasing. We still have the vertical asymptote of x equals 0 for the log function. Domain is still everything greater than 0. Range is still all real numbers. We're still passing through that same x-intercept, 1, 0. Right. Right, so you need to be familiar with the graphs of these functions, and once we have a new function, what do we like to do with it? We like to translate it, right? Do a transformation, shift it up, down, left, right, do reflections about the in the x and y axis and in the origin, and vertical stretches and so on and so forth. So let's see how the following graphs are affected, give their domain, range, and vertical asymptote now. All right, so how was the graph of g of x obtained from log base 2 of x? Formula-wise, I simply replaced x with x minus 4. So this is a shift where? Left, right, up, or down? Take a guess. What do you think? Hopefully you know. You're not guessing. It should be a shift right. Remember, replacing x with x minus 4 shifts right 4 units. That was that kind of weird thing. You see x minus 4, that seems like it should go left. No, you're replacing x with x minus 4. Okay, and be careful. If it was parentheses closed around the x and then this minus 4 was outside, that would be a shift down, right? If we had the negative 4 outside. Right, this is inside the log function here. So this is a shift right, not a shift down. All right, what's the domain? Well, the domain was everything greater than 0. Everything greater than 0, right? But now we shift right 4 units. So what's the domain now? Everything greater than 4. Everything shifts to the right. The range, well, shifting to the right does not affect the range. It's still all real numbers. What's the vertical asymptote? Well, it was at x equals 0, right? That was the y-axis. Now everything shifted 4 units to the right, so now it's at x equals 4. And what's the x-intercept? Remember, it was at 1, 0. Now what? Shift it 4 more units. It's what? 5, 0. Okay. What's the graph of h of x? How was it obtained from the graph of log base 2 of x? Well, reflection in which axis? Replacing x with negative x means the y-axis, right? We reflect about the y-axis, right? So going back to our graph of log base 2 of x, if I reflected about the y-axis, what happens? It's now doing this sort of thing, right? It's now here. So the point 2 comma 1 becomes what? Negative 2 comma 1. The point 4 comma 2 becomes negative 4 comma 2, right? And the graph will look like that, reflecting in the y-axis. So how's that going to affect things? The domain was everything greater than 0. Now reflecting about the y-axis, it's what? Everything less than 0. The range was all real numbers. Well, reflecting in the y-axis does not affect that. Right? We're still all real numbers. Right? So if I do the reflection again, the range is still going to be going to positive infinity this way and down to negative infinity as we approach this vertical asymptote, which the vertical asymptote, notice, hasn't changed. It's still x equals 0. We're just approaching it from below, or from negative side here. Okay? So the vertical asymptote is still there. And what happened to the x-intercept? It was at 1 comma 0, now what? Reflecting the y-axis, now at negative 1 comma 0. Okay. What about this function? This was obtained from the graph of y equal to the x, log base 2 of x rather, by a shift what? 3 units what? Up. Shift up 3 units. Because we have log base 2 of x and we just added 3 to it. Doesn't matter the order, right? So log base 2 of x and then add 3. Notice this, it's not like here where we've done it inside the log function as an input. We replace the input x with x minus 4. Here we just add 3 to the output. So if we shift up, does that affect the domain? No, it does not. It's still everything greater than 0. Does that affect the range? No, it does not. It's still all real numbers. Does that affect the vertical asymptote? No, we just slide upward, so we don't shift left or right. The vertical asymptote is the same. But it is going to affect the x-intercept, right? If I take this this purple graph, there's our x-intercept. If I shift this up, what's going to happen? Our x-intercept is going to shift this way, right? It's going to shift this way. So what is that x-intercept? Okay. Well, again, it's easy to find the x-intercept if we just plug in 0 into the function, right? Sorry, that is wrong. That's the y-intercept. I'm going crazy. I want to find the x such the output is 0. Sorry, x-intercept. We want to find out the value of x that makes the output 0. All right, and so what are we talking about? The output to the function is 3 plus log base 2 of x. We want that to be 0. Okay, so what value of x will make this 0? So it's a little bit harder again. If I was looking for the y-intercept, which, by the way, there is no y-intercept because look at our domain, everything greater than 0, so x cannot be 0. So I made a double mistake there, a really bad mistake. But the output to the function being 0 tells us what the x-intercept is, right? What's the value of x that puts us on the y-axis? Well, this statement will be true, right? If log base 2 of x is what? Negative 3, right? 3 plus negative 3 is 0. So if that logarithm is negative 3, we're good. So what is x? Well, remember, this is the logarithmic expression. What's the exponential expression? Well, log base 2 of x equal negative 3. Log base 2 of x, right, is negative 3. That logarithm, negative 3, that's what? What is a logarithm again? A logarithm is what? The exponent. Exponent on what? The base, right? So that means x is what? 2 to the negative 3 power. And therefore x is what? 1 divided by 2 cubed, which is 1/8. So there's our x-intercept. And notice that makes sense that the x-intercept is 1/8 comma 0. So when I take log base 2 of 1/8, I get negative 3. 3 plus negative 3 gives me 0. And that's exactly what we said, right? We shifted this thing up 3 units, and as we move this graph up, this x-intercept slides over this way. Okay. Let's look at some basic properties of the logarithm. So, for any base, log base a of 1 is always 0. Why? Because a to the 0 power is always 1. There's the corresponding exponential expression. Log base a of a is 1. Why? Because the power of a needed to get a is 1. A to the first power is a. Log base a of a to the x is x. Why? Because a, well, you answered this question. A to what power equals a to the x? You know, what goes there? Duh, x, right? In other words, what we're saying is log base a of a to the x. What's the power on the base a needed to get a to the x? It's x. Another way of thinking about this is we've composed, if you remember a composition, we've composed two functions together. The first function is the exponential function, a to the x, and then I applied log base a to that. So there's like a parentheses around this, right? And they cancel each other out, right? So log base a of something, right, is the power of the base needed to get that something. So what is the power on a needed to get a to the x? Answer x. Or again, they use inverse functions that cancel each other out. Now here, look at this one. A to log base a of x equals x. Again, this is the inverse relationship. If I take the log function at base a and plug x in, get my output, and then plug it into the a to the x function, or a to the u function, or whatever, I get back to the original input x. Or another way of thinking about this is, what is log base a of x again? We said what? Log base a of x is what? An exponent, right? Logarithm is an exponent. So log base a of x is the exponent on the base needed to get x. Log base a of x is the exponent on the base needed to get x. What is the base? A. So if I raise a to this power, log base a of x, I should get x. That's what we mean. And so we raise a to that power, what do we get? X. So these are the inverse relationships here. And they're going to be key when we're solving logarithmic and exponential equations. Because when we solve equations, we apply inverse functions. So what is log base 50 of 1? Answer, 0. What is log base 3 of 3 to the 7th? Answer, 7. What is 2 to the log base 2 of 7? Answer, 7. Right? So these are using the properties we just talked about. Now, if I wanted to find logarithms of values, like say I wanted to find log base 10 of 71. Log base 10 of 71. Right? Well, let's think about log base 10 of 71. Right? What is that? Equal to x. Well, then that means 10 to the x power is 71. Now I know 10 to the first power is 10. 10 squared is 100. So the number here must be between 1 and 2, but I don't know what it is. What's the power of 10 to get 71? I don't know. And so we do have some help with technology now that we can use. In the TI calculator, there are 2 logarithmic keys, if you will. One, and most scientific calculators you'll have this as well. The common logarithm is log base 10 of x, okay, like I've got here. But typically, we don't write the 10. We usually just write log without a subscript. And what does that mean? Well, this is what we call the common logarithm. If you see logarithm without an exponent, then that means log base 10. And so if I say log of 71 equals x, then what I mean is 10 to what power gives me 71 again. So same thing as here. Notice I don't have the subscript that means the same thing. So I can actually find in the calculator that button. All right, you can see here log, and notice it's connected to the 10 to the x. Right, they're inverse functions right there in the calculator. So if you want to raise 10 to a power, you got that, and then you want to find the power on the base, need to get some value where the base is 10, use the log button. So if I use the log button, let's turn this on. Turn it on. If I use that log button, it comes up like that. And then if I want to take log of 71, I can approximate it. There it is. And as I said, I knew it was something between 1 and 2, right? The power of 10 needed to get 71. And as a check, let's just see. If I take 10 and raise it to this power, now I've got to be careful not to round. And so the way I'm going to do that is I'm going to use the answer, ANS. I don't know if anyone has seen that before, but answer, ANS gets the value that you compute each time it's updated. Let me clear this out for a minute. If I just do second and then hit that little minus sign, which is answer, right, then hit enter, it just stores the value, whatever, after you hit enter, that value is stored into answer. So if I now take 10 and raise it to the answer power, what should I get? What should I get? 71. I get back to what I started with. Okay. Now be careful if you round that off, right? If I said, oh, that's about 1.85, okay, well, you're going to get rounded off value. You're not going to get close to exactly 71. So there's some round off even in this value here, but it usually is going to, if you round it off too much, obviously you'll be off a little bit. So we can do logarithms base 10. We can also do logarithms base e. You remember the natural exponential function, right? The one with base e, e to the x. Well, the natural logarithmic function then, with log base e, this is usually written ln of x. And ln is an abbreviation for logarithmic natural, French rendering, and so ln is typically used for this logarithm. So when you see ln, that's really log base e. And so ln is log base e. Right? So for instance, if I wanted to find that key, first of all, you'll notice it's right here, right connected to e to the x, which is good, right? So if I do natural log of e to the 5th power, what am I going to get? What am I going to get? Well, it's going to cancel each other out. In other words, right, what's the power on the base e needed to get e to the 5th? E to what power is e to the 5th? Answer 5. Okay. But if I want to take the natural log of something like, 2, what's the natural log of 2? What's the power of e needed to get 2? There it is. That's the power of e needed to get 2. So if I take e and raise it to that power, I'll call that answer, right? That's stored in the answer variable. I should get 2, right? And I do. Now, the graph of the natural exponential function is shown here, right? Remember graphs of logarithmic functions where the base is greater than 1 look like this, right? And so what are the coordinates for the indicated points? Well, obviously this point is what? As is true for all, 1, 0 is the x-intercept for all logarithmic functions. And that's because what? The power on the base, which is e, needed to get 1 is 0. E to the 0 is equal to 1, therefore the natural log of 1 is 0. So again, we e to the 0 equals 1, and therefore the natural log of 1 is 0. I like to put parentheses around that. Again, it's like a function. This is not ln times 1. This is natural log of 1. A lot of times they don't write the parentheses there. Well, what about this one here? What's going to be this coordinate? Obviously, the output is 1, right? The output is 1. So notice if I take e to the first power, I get e, right? And therefore, the natural log of e is what? What's the power on the base e needed to get e? E to what power equals e? Answer 1. And so the coordinates of this point is e comma 1. Right? Remember, e is about 2.71128. There it is, right? The properties for the natural logarithm that we looked at above for arbitrary bases is true. So natural log of 1 is 0, natural log of e is 1, natural log of e to the x is x, and e to the natural log of x is equal to x. Let's evaluate the following expressions with this idea then. What's log of 0.001? So what's the corresponding, what is log? There's no base. What does that mean? No base means base is 10. So 10 to the x, what I'm looking for, the logarithm, is what? 0.001. Now, what is 0.001? This is the tenths, hundredths, thousandths, right? This is 1,000th. Right? 1,000 is 10 to what power? 1,000 is 10 to what power? Third power. Right? But 1 divided by 10 to the third is what? Negative 3. And so log of 0.001 is negative 3. And you can kind of think what's going to happen, right? If it's, what if it was 0.0001? The 1 would be in the fourth decimal place. Well, it's going to be negative 4. So it's whatever position. If it's 0.1, log of 0.1 is negative 1. Log of 0.01 is negative 2. Log of 0.001 is negative 3, and so on. Similarly, if I said, what is log of 100, what would your answer be? What's the power of 10 need to get 100? Well, that's easy. The answer is 2, right? Because what? 10 squared equals 100. What's the natural log of e to the fifth? 5. Just making use of that property right there. What is 10 to the log of 3? Answer, 3. Those are inverse functions there, right? Log, what base? 10, right? Because there's no base. So this is a common logarithm, base 10. And then 10 is raised to that power. Remember, log base 3 is the power of 10 needed to get 3. So if I take 10 to that power, I get 3. What's e to the natural log of pi? Answer, pi. Again, they cancel each other out by this property here. Okay, so logarithms, very useful, we're going to see. So we need to be able to manipulate and play around with these logarithms and evaluate them. What we'll look at in the next videos, we'll talk about the domain of the logarithm and how we can find domains involving logarithmic functions.